And we're rolling. All right, so we're going to introduce some notation with vectors. Talk about components of the vectors, all kinds of good stuff. So vectors 2 is the title. Component form, I think, is what well, that's the label there. Component form of vectors. Component is a word which just means the part. If we break a vector into its parts, you're going to have the x part, you're going to have the y part. So let's go ahead and talk about a vector. Now I'm going to draw a vector starting at the origin. I'm just going to kind of go up and to the right. I'm going to call it vector A. And its x part, its x component, is going to be a length of 1. Its y part is going to be a length of 3. Sometimes I will call this AX, like A and then a subscript x, so A little x, and AY for the y component. That blue didn't work out very well, so we're going to push it over here. Let's try this red. Now this starting point is what we call the initial point. The ending point, well, it makes sense to call it the ending point, but we don't call it the ending point, we call it the terminal point. Our initial point, when my vector is located here, has the coordinate 0, 0. Does anybody want to make a guess what the terminal point coordinates are? 1, 3. Yep. And if we were talking about this vector, we have some notation that we use. We use these angle brackets thing. There's like less than, greater than thing, where we have the less than angle bracket, and then you have the x component, comma, and the y component, and then the other angle bracket. Now, that does not mean that my vector is always going to end at 1, 3. It just means that the vector goes 1 unit to the right and 3 units up. If you remember, we should be recording it. A vector can be moved wherever you want it to be. Okay, and when we had that one application, we were clicking on the vector and then dragging it all around. In fact, I could grab this vector and draw it over here so that this is the initial point, and it's going to look, look something like that. It's still vector A, and it still has 1 unit horizontal and 3 units vertical. Okay, it's just located over here now. Its initial point is whatever this coordinate is, and its terminal point is going to be whatever this point happens to be. Does that make sense? So in the event that you drag your vector over here to the origin, okay, so that it starts at the origin, then and only then is the terminal point, parentheses 1, 3, equal to the vector in component form, angle bracket 1, 3. All right? This is what's called component form. The other day when we had like vector A equals 5 miles at 20 degrees. That was standard form. Do y'all remember what this first number meant in standard form? That was the magnitude, and this second number was the direction. Okay? So that's one of the things about vectors, is that we have two ways of talking about them: component form and standard form. The x and y part, and then also we could talk about the magnitude and the direction. All right, let's kind of dig a little bit more into initial point, terminal point. Mr. Great Sword Buddy there, if you don't mind, go ahead and cue up the homework.
Okay, what's it?
Brianna?
Brown's here, Nayeli's here, Ferrari. All right, let's just, I'm going to draw a vector right here. It's kind of middle of the first quadrant. I kind of like going up and to the right there. This will be vector B. And it's going to have an initial point, x1, y1, and a terminal point, x2, y2. So you can imagine it has a x component, a y component. We'll call that bx and by. Let's see if we can come up with a formula here for bx. So bx is this length right here. Anybody have an idea what utilizing these terms for bx? Shall I put some numbers in there to make it easy for you? Or Preston says maybe it's x2 minus x1. Let's see if you're right. Let's just say that this happened to be at position 3, and this happened to be over at position 10. Okay? Well, the difference between 3 and 10 is 7. In fact, the way that we find that is the difference. Do 10 minus 3. So, yeah, that seems to make sense to me. And then by, y'all can probably imagine, same sort of idea, y2 minus y1. So let's say this happened to be at a value of 1, and this one happened to be at a value of 9. That vertical part would be 9 minus 1, so it would be 8. Yep, that looks pretty good. So we can write a vector b in component form as angle bracket x2 minus x1 and y2 minus y1. Those angle brackets there. All right, all kinds of good stuff we're learning about vectors. So, another coordinate axis there. Sure, up and to the right, why not? There's vector C. And we have CX and the CY. Let's go ahead and I'll throw some numbers here. Let's say we've got 3 for the X component, 4 for the Y component, and if y'all remember your Pythagorean triples, that's going to be 5. Because 3 squared plus 4 squared is 5 squared, so 5 for the magnitude. All right? So we could say vector C in component form is angle bracket 3, comma 4. What I want to talk about is what happens if we multiply that vector by 2. In other words, what happens if we have 2c? Now, we did talk about this earlier this week. when you multiply a vector by a scalar, what changes, class? The magnitude, the direction, or both?
Wait, repeat that.
When you take a number and you multiply it by a vector, okay? What changes about the vector? Does the magnitude change? Does the angle change? Or do both change?
Magnitude.
The magnitude changes. So 2c would be in the same direction, but double the magnitude. So same direction, but 2 times the magnitude. I tried to make those kind of the same. Alright? Well, if this had a magnitude of 5, then the magnitude of 2c is going to be 2 times 5. So that's going to be 10. And in fact, it's essentially the same as if you took vector c and then another vector c and added them together. Alright, but c plus c is equal to 2c. And as you can see, the x part of 2c is going to just be 3 plus 3, it's going to be 6. And the y part, 4 plus 4, that's going to be 8. So if I write 2c in component form, that's going to be angle bracket 6, comma 8, close angle bracket. Alright? Now that leads us, if we kind of think about this, well, what if there was 3c? What do you think that would be? I mean, I can draw it all the way out, but you can see that it's going to be 3 times the original vector's magnitude. The x component would be 3 times bigger, and the y component would be 3 times bigger. So it'd be 3 times 3, which would be 9, 3 times 4, which would be 12. Can y'all see that?
So you will always go back to the original?
Yeah, absolutely, yeah, because it's 3 times vector c. So the rule is, in fact, for rules, I kind of tend to put them over here. So Mr. Creature might need to follow me over here. If you have vector v with an x component vx and a y component vy, and then you have k, which is some constant, some number, and you multiply it by vector v, then the new vector is just going to be k times vx, k times vy. So this is a scalar vector multiplication, or multiplying a vector by a scalar. How do you do it? Well, one way that we did it the other day is you could take that scalar and multiply it by the magnitude, and you're going to get the new magnitude will be in the same direction. But if you're given your vector in component form, then you take that k and multiply it by the x component multiplied by the y component. Just to make things a little bit clearer. If we have vector d, all right, and that is 10 miles at 30 degrees. Now this is what form is this in? Component form or standard form? Standard form. Now when you have standard form and you have, 7 times d, what we said is you take the 7 and you multiply it by the magnitude, so 70 miles, but the direction stays the same. So in other words, if you have vector v is equal to some magnitude m, actually no, we use r, and some direction theta, and you have k times vector v, anybody want to guess what we're going to put right here? K times r. Just theta, exactly, yep. So this is multiplication when you have component form. This is vector multiplication when you are in standard form. One more thing, dealing with component forms, then we'll go to the problems. And that's adding up two vectors. And we already kind of saw this the other day, but we'll make it nice and algebraic here now. So let's say I've got vector A, and then on the end of it, I've got vector B. So we've got AX AY BX and BY. Vector A is AX, comma AY. Vector B is BX, comma BY. And then we've got vector C, which is equal to vector A plus vector B. So remember, the way that you add two vectors is you draw one vector, and then at the end of that vector, you draw the other vector, like that. And then you connect the beginning of the first one to the end of the second one. And so that's vector C. And so you see that it has CX and CY. Like I said, we talked about this the other day, but now we're just sort of kind of making things a little more formal, putting letters to all of this. So what do y'all notice about CX? Say it again, Preston. Yeah, it's AX plus BX. It just kind of makes sense. If you've got two things you're added up together, and those two things could be broken down into their parts, their X part and Y part. You just take the X part of this one and the X part of that one, and that's going to give you the X part of the answer. So CX is equal to AX plus BX. Ladies, what do you know about C, or what do you notice about CY? Yeah, it's AY plus BY. So Naomi, I'm going to ask you a tricky question, all right? When I'm looking at like the horizontal part, the x part of A, right? So how much is going left and right, not at all is up and down, okay? And I look at the horizontal part of B, so it's just left and right, okay? Is that affecting the vertical part of C at all? Because it's not that tricky of a question. Yeah, it's not. The horizontal parts of A and B only affect the horizontal part of C. And the vertical parts of A and B only affect the vertical parts of C. Okay? What's interesting about that is how it relates to projectile motion. Okay? You get something that's actually kind of counterintuitive. In other words, it's not what you would expect. Okay? Well, let me show you what I mean. Let's say I've got two situations in which I am throwing an object. I don't have my juggling balls in here, but I do have these markers. Okay? So I'm going to throw this marker as far as I can across the room, or maybe even down the hallway would probably be better. Okay? So in both situations, I'm going to be launching it at the same angle, okay? One of them I'm going to be, so they're both launching along this line, okay? At maybe say 40 degrees, okay? But one of them is going to have, you know, an X component. Hold on, let me do something a little bit better. Let me just put it this way. When I'm throwing something, okay, and I'm throwing it really, really hard horizontally, or I'm throwing it kind of soft horizontally, neither one of those are going to affect how fast it's falling vertically. That make sense? Because I'm just throwing horizontal, you know, I mean, and I can throw it up and down, something like that, depending on how hard I throw it up, how hard I throw it down. But the idea is that the horizontal part is not affected by the vertical part at all. Okay? I'll draw. Let me give you a better example here. So, if I do throw something, and it kind of travels like this, and it has an initial velocity vector, and it has a Vx and a Vy, that horizontal velocity vector is the same throughout the entire time of flight. If I throw it and horizontally it's traveling 1 foot per second, it's going to be traveling 1 foot per second, 1 foot per second, 1 foot per second, 1 foot. It's going to be traveling at that rate horizontally the entire time. The horizontal velocity, how fast it's going this way, is not affected by gravity at all. There's only one part of its motion that's affected by gravity, and that is its up and down part. Okay, so that's kind of a neat thing, where it doesn't matter how you know, how far, you know, how much horizontal velocity you have, it's still it's vertical velocity. So let me give you an example here. So what I can do is, if I drop both of these pens at the same time, okay, then they're going to hit the ground at the same time, obviously. Okay. But if I take this pen and I'm not going to throw it up at all, but I'm going to just throw it horizontally, okay, all right, and the same time I let it go, I'm going to let this one go, all right. What actually happens is this one is right here. I give it a really strong horizontal velocity, it's going to go like that. And the other one, I'm going to release it, and it's going to go straight down like that. The horizontal velocity, you might think that the purple one is going to take longer to hit the ground, right? Because I'm throwing it out that way. But in reality, it doesn't. Because the horizontal velocity doesn't affect it's up and down velocity. They actually both hit the ground at the same time. Let's see if I can show you. Did you catch that? Maybe not. Mind you do it again. And we're underneath the thing. So in other words, what you would expect is that because I'm giving this more horizontal velocity, you might expect that it's gonna land later. But the fact is I could shoot this one out of a bullet, okay? Or out of a gun, I could shoot a bullet out of a gun, and at the same time drop this one, and they will both hit the ground at the same time. Because the vertical velocity does not depend at all on the horizontal velocity. And they've actually done this sort of thing in like Mythbusters and things like that, where they've shot a gun, they've shot a bullet, and at the same time they've dropped a bullet, and they both hit the ground at the same time. Because the horizontal and the vertical, they don't affect each other. Okay? Try that one time. And it's down the ball. Let's go and do some problems together. It wasn't going to roll under the door, but it kind of looked like it was. Mr. Greensword, where are those papers? Where's the next? We're going to be drawing some pictures on these. Number one, it says find the magnitude of the vector -3, -6. So this is its x component, that is its y component. -3 means it goes to the left. We're just going to draw all of our vectors starting at the origin, if that's all right. I think that's going to make things a lot easier for us. So 3 and then down 6. 1, 2, 3, 4, 5, 6. There's the vector. We can put -3 right there. We can put -6 if we wanted to. And then want to find the magnitude. So remind me, class, what does the magnitude correspond to on the picture? Where is the magnitude? Yeah, it's R. How are we going to find R? Yeah, say louder there. They can hear you on the video. Okay, Pythagorean theorem. It's the answer to 90% of the questions in this class. So, yep. So we've got, if you want to put -3 or +3, doesn't matter, we square it anyway, and then the -6 squared is going to be R squared. So 9 plus 36 equals R squared.
Do you want it as a decimal or?
Good question. Answer says, write your answer, or the question says, write your answer in simplified radical form. So 36 plus 9, that's 45. Is R squared, so take the square root, so square root of 45. Oh my gosh, first week of school. Go back to simplifying radicals. We can break that 45 down into 9 times 5. And then we can split that up into the square root of 9 times the square root of 5. So 3 square roots of 5. Seems pretty good to me.
Were we just trying to find R?
What did they ask us for? Find the magnitude. Okay. Boom. Got it. Let's move on. Are y'all okay if I leave number 2 alone? Like that's kind of pretty much the same thing?
Yes.
All right. If we want to, we can come back to it, but let's make sure we cover one of every single type here. Number 3, a vector has an initial point, 2, -3, and a terminal point, 3, -4. Write vector W, they always got to make it both in component form. Okay? If you want to draw a picture on these to kind of get a reality check, I think it's a good idea. Initial point 2, 3, so 1, 2, sorry, 2, 3, 1, 2, 3. Something like that. And terminal point 3, -4. So 3, something like that. That's almost enough right there to be able to tell what the x and the y components are. In fact, I could think, anybody want to guess what that x part is? Going from 2 to 3? 1. What about going from -3 to -4?
Well,
It is a distance of 1, but direction counts.
oh,
So since it's down, it's -1. All right. Now,
could you just do,
can we do the formula?
yeah, like the, instead of,
Yes, and I want to do it both ways. So this way, I just kind of drew it and was kind of like, oh my gosh, that's really basic. And if you can do that, that's great. But let's use the formula: x1, y1, x2, y2. So the x component, wx, is x2 minus x1. So 3 minus 2, which is 1. The y component, y2 minus y1. So -4 minus -3. Now remember, the formula says this number minus that number. So put that minus sign in there, and then the fact that this other number is negative, well, we're supposed to put it in parentheses here. So -4 minus -3 minus the negative number turns into plus, so -4 plus 3 is -1. And that matches sort of what we concluded. All right, any questions? I think you're gonna like this homework. Hopefully, I don't know, maybe you have some vector problems available on your pie chart. Maybe sort of, I don't know. It'd be good for your 10 topics. Let's go to number 5. Given the vectors A, which is 0, 8, and B, -3, -7, find 2A and A plus B. Write your answers in component form. So 2A, if you remember, is going to be 2 times whatever the x component is, so 0, and 2 times whatever the y component is, so that's 8. I'm getting this from this right here, where if you have a vector in component form and you're multiplying it by a number, you just take that number, multiply it by the x component, take that number, multiply it by the y component. In this case, it's almost trivial because 2 times 0 is still 0. 2 times 8 is 16. So that is 2 times vector A. And then A plus B, well, from what we saw here, which I don't know if we really gave a nice summary example. Let me write one nice summary sentence here. If C is equal to A plus B, then C is equal to AX plus BX in the X component, and then AY plus BY in the Y component. Sorry, I got so excited about talking about projectile motion. We didn't write a nice summary, but I feel like this also kind of communicates that, but there it is all in component form. Almost in formula form. So when I have 2 vectors added there, so the new vector is going to be AX, so the 0, plus BX, which is -3, comma, AY, which is 8, plus BY, which is -7. So 0 minus 3 is just going to be a -3, and 8 plus a -7 is 8 minus 7, so that's going to be 1. let's see if you can do these almost in your head for this next one. M is 2, 0, N is negative 6, negative 5. What is 6M, class? 12, 0. And what is M plus N? That'd be tricky, but I'm sure you can handle 2 plus a negative 6. Negative 4. 0 plus negative 5. Negative 5. See? You can finish your homework in 5 minutes. Alright, let's look at the back there. Now, what is different about these problems?
They're negative numbers.
Yeah, we do have negative, yeah. And let's just read it here. It says, given vector A is negative 5, 1, B is 4, 3, find 5A minus 3B. This is what's called a linear combination of vectors, okay? We're taking some vector and multiplying it by another number, and then taking the other vector and multiplying it by some number and kind of combining them, okay? But you know what? We can handle this no problem. So, 5 times vector A minus 3 times vector B. And I'm going to kind of show you a little bit of a different way of thinking about this maybe. So this is 5, and then I'm going to write vector A here as angle bracket negative 5, 1, minus 3, and then for B I'm going to put angle bracket 4, 3. Alright, now subtracting vectors, just like in math, subtracting numbers is the same thing as adding the opposite. So what we could do is we could just put a plus right there and say this is adding the opposite of this one. And so we'll deal with each part individually. 5 times vector A, just based on our formula over there, it's going to be 5 times the x component, so negative 25. 5 times the y component, so 5 times 1 is 5, plus, same kind of thing over here, we've got a scalar times the vector, so negative 3 times the x component, so negative 3 times 4, it's going to be a negative 12, negative 3 times 3, negative 9. And then we're adding the vectors, so we literally just add the x components and add the y components. Don't tell any Algebra 2 students this is what we're doing. They'll be jealous. Alright, so negative 25 plus negative 12 is?
Negative 37.
And then we have 5 plus negative 9, so 5 minus 9, yes, you're right, negative 4.
So when you're subtracting, when it says subtract, you can just
add the negative. That's the way that you do it. Vector subtraction, I guess I didn't tell you how that works, but you basically it's take the negative and add it. So, yep, that's the thing to notice on that one. Do we think we could almost do this one? Let's do number 8 together just real quickly, because we've got time. So it's going to be negative 3a plus 4b. So we might be able to kind of simplify it. Negative 3a, let's just go ahead and do that when we write it down first. So it's negative 3 times the x, negative 3 times the y. So what's the new one going to be? Negative 3 comma 18, yep. Plus 4b. 12, 8, yep. And then add them up. Add the x's, add the y's. Negative 3 plus 12. 18 plus 8. that's in component form. All right. So class, today we talked about component form, sort of kind of looking back through this. We talked about combining vectors that have been multiplied. We talked about just how to deal with vectors that were multiplied by a scalar, all in component form. We talked about how to find the component form given an initial point and a terminal point. And we talked about how to find the magnitude of a vector given component form. All kinds of stuff here, right? But not very difficult. Just as a sort of a concluding, sort of reflective thought, we don't really live in a 2D world. We live in a 3D world, and there is a whole system of mathematics based on three-dimensional vectors, and it's really cool. And it really, for the most part, it's just adding one more number at the end of here, an x, a y, and a z, and almost all the formulas are the same. Okay. Preston, obviously we see a lot of that in Blender and in Unity, in 3D graphics programs, 3D game design programs. There's a lot of business, a lot of jobs out there that use 3D vectors. Shoot, there's a lot of jobs out there that use 2D vectors, all right? But this is not just sort of just math stuff. There's lots of real applications. All right. Good job, y'all. Screen through if you don't mind.